It's nice to finally get to interact with you and meet you and teach and see a little bit how you're doing. So I would like to introduce you Wagner, who is sitting in the back there. He's a postdoc here at ICTP from Brazil. Maybe some of you know him already. And he will be doing the tutorials and the exercise classes for the class, maybe together with me or maybe on his own. And maybe sometimes if you have questions, you can go to his office. Also, it's just opposite my office. And we have not scheduled the times yet, but between today and tomorrow we'll fix some times for the next few weeks. During the course there will be some breaks because I have some trips, but we will see that as we go along. Now for the next couple of weeks we have 3 lectures every week. So this is a Introduction to Dynamical Systems course. The way I will do it is I have, as you know, in every mathematics course the exercises are very important. In my case even particularly so, they really are an integral part of the course. So some of the results, I think it's no point me spending 20 minutes or half an hour giving you a proof when you can kind of develop it for yourself with some guided exercise. I think it's much more fruitful. So I have some notes which I will send you the link or the PDF of these notes, which every year I change a little bit, but I follow fairly closely, not every section. So there's some sections we will skip, but I will send you the notes. It contains also the exercises. So you should really do all the exercises unless I tell you so, at least of the sections that we cover. Okay, it's very important. The course has 2 parts. More or less half of the course will be on a more topological aspect of dynamical systems. You will see what I mean when I start telling you. The second half of the course will be more ergodic theory, which means more using the language of measure theory and probability. Okay, because it studies the statistical aspects of dynamical systems. Okay, I think that's everything in terms of general administrative information. Do you have any questions? So I'm very happy if you ask questions during the course. I encourage you. I will ask you lots of questions. So in exchange you can ask me also lots of questions. Okay? Especially if you don't understand something, it's very important. Now in this field, as you shall see, it seems very simple at the beginning because there is no very sophisticated objects. But you have to pay attention because it's not as obvious as it seems. Okay? So the setting is really, really very basic. We have a set X. And we have a map. F from X to X. So it's really the simplest possible setting. What does that mean that we have a map from X to X? So here we have our set X. And a map means that you take some point here, let's call it X0, and you apply the map. Right? So the map is a map from X to X, so it gives you for each point of X, it associates another point of X, right? So we apply the map F, and we get another point which we can call X1. F of X0. Obviously, this is true for any point. So any point you choose, so you take the point Y0, you apply the map, and you get Y1 is equal to F of Y0. Okay? And then you can do it again. So you can take this point X1, and you apply the map to this point, and you get another point X2, and then you apply the map again, and you take a point X3, and so on. So you iterate this map, right? So we write Fn of X is just a composition of these maps, because we're composing a map n times applied to X. x0, let's say. Okay, and what this composition means is just a composition of maps. So you take the point x0, you apply f, you get a new point, then you apply f to that, then you apply f to that, then you apply f to that. Okay? And what we get is a kind of evolution. So the idea behind the dynamical system is that it's a system where something evolves in time. So the choice of your x0 is kind of an initial condition. You can choose this initial condition or this initial condition. And depending on the initial condition, the system evolves according to a certain rule or a certain law which is defined by f. Right? So it evolves because if at time 0 you're here, at time 1 you're here, at time 2 you're here, at time 3 you're here, and so on, and it evolves. If you start from y0, then it may evolve in a different way. Okay, so we will give lots of specific examples, but first, just in this very abstract setting, there's already a few things you can say, which is that there are some, so the orbit, we define the orbit, so the forward orbit of x0 is the set fn by 0 for n equals 0 to infinity. Right? Because you can keep doing this. So
do you require the f to be invertible?
That's right. So not necessarily. So this I write this is the notation I will use for the forward orbit. Now, if f is invertible, that's a very good question, thank you. So if f is invertible, then we have the map. So if f is invertible, invertible means it's a bijection. Bijection. Then f minus 1 is defined. Then we have f minus 1 is also a map from x to x. Which means that there is an inverse, which means that x0 itself comes from some x minus 1. Right? And then here there's some x minus 2. These are the backward images of x0. Okay, then we say the orbit, the full. Usually this is clear from the context, but sometimes we call the full orbit is equal to x0, and this we can now write as fn of x0 for all n from minus infinity to infinity. You can take the forward part of the orbit and the backward part of the orbit. Any questions about this? Is this all clear? So before I start giving some examples, because otherwise it stays very abstract, let's immediately say there's some very special cases of orbits, right? So if f of x0 equals x0, then x0 is called a fixed point, because x0 maps to 0. It's a fixed point. If fk of x0 equals x0, so it could be, for example, that x0 goes to x1, goes to x2, goes to x3, and x3 maps back to x0. Then this is called a periodic orbit. Of period k.
Do we call x0 a periodic orbit, or we call the period orbit of x0 a periodic?
A periodic point is a periodic point, thank you, yes. Is a periodic point, and the orbit is a periodic orbit.
But do we assume k to be the smallest?
Thank you very much, that's also a very good question. So notice that, of course, a fixed point is also a periodic point for every k, right? Because if it's a fixed point, then fk of x0 is also x0. So it is formally correct to call this also periodic point of period 5, but obviously does not really give you enough information. It gives you kind of, so sometimes we call the minimal period is really the minimal period, right? So k is the minimal period if f I of x0 is different from x0 for all I equals 1 k minus 1. In other words, because this is a period 4, this is a periodic point of period 4, but it's also a periodic point of period 8, of course. But 8 is not the minimal period, right? Because for I equals 4, we don't have this, so it's not the minimal period. Okay, so this is really the fundamental first definitions that we need to start studying some examples. As you see, it's really, there's no structure. I will now introduce, in all our examples, we will always have X to be a metric space, at least. And when you have a metric space, you can start introducing many more things, like the accumulation points of orbits and so on, which I will introduce in a second. But I do want to emphasize that the basic fundamental concept of a map and iterating a map and even fixed points and periodic points, they really do not need any structure at all, just a set and a map. Okay, so let's see some first basic examples, and then I will also introduce the other definitions. Okay. So as the first example, let's suppose x is the real line. And let's take f of x equals 1/2 of x. So, does this map have any fixed points? Yeah, obviously 0 is a fixed point. It's f of 0. Does it have any other fixed points?
No.
No, because clearly if you take a point and you take half of it, it's not going to be the point itself on its axis. So what do the orbits look like of this point? If we take a point x0 here, where is x1? Half of x0, right? So f1 will be somewhere here, so we apply f, we get x1, we apply f again, we get x2, and so on. And the same from this side, right? If we take y0 here, it will map to y1, which is half of this. In fact, here, in this very special case, we have a precise formula, right? Fn of x equals 1/2n x0. Exactly. Okay? So what does the orbit of x look like? The forward orbit of some point x0. What can you tell me about this forward orbit? How would you describe this forward orbit? What can you tell me about this sequence of points? An orbit is really just a sequence of points.
Always converge to 0?
It converges to 0. Everyone sees that? Yeah, this is clear. So it converges to 0. So notice that Fn of x, 0, converges to 0 as n tends to infinity for every x0, every initial condition. What if we take, let's generalize this a little bit. F of x equals lambda x, okay, where lambda can be something, various cases. So if lambda is, so let's suppose lambda, so what are the various cases here? Let's take, for example, lambda between 0 and 1. So let's write the various cases here. Lambda between 0 and 1. What happens? So first of all, for any lambda, so lambda is a parameter, right? So each one is a different dynamical system, different map. We're just studying the different cases. So when lambda is, for any lambda, when lambda is 0, what happens? Everything maps to 0. Okay? That is still, okay. It's still a dynamical system. It's still a map from R to R. Okay? Everything maps to 0. And what does 0 map to? 0 itself. Okay? So 0 is a fixed point, and then everything maps to 0. Okay? So this actually brings me to make another definition, which I did not make before, but this is a good moment. So lambda equals 0 implies f of x equals 0 for all x. Okay? And then let me say that x is a pre-periodic point. So x is pre-periodic if fk of x is periodic. In other words, in the case when the map is non-invertible, you may have this situation where you have a point that is not periodic, but after some time it lands on a periodic point. Just like in this case, when lambda is equal to 0, all these points here are not fixed points, but after one iterate, immediately they land on 0, which is a fixed point. And then they stay on 0 all the time. Okay? We shall see many other examples in which you might have a periodic point, and if the map is non-invertible, you might after some time land on that periodic point, and then you stay on that periodic point. Why am I insisting that the map should be non-invertible for this to happen?
Because if it is invertible, any pre-periodic would be itself a periodic.
Exactly. If it is non-invertible, then this periodic point will have only one pre-image, and this one pre-image will be a point of the periodic orbit, right? It will be its pre-image. It will be the point that maps to itself in the periodic orbit. Okay? So if the map is invertible, I think there's an exercise just to clarify this, but remember, if the map is invertible, you cannot have any pre-periodic points. Either it's periodic or it's not periodic. Whereas if it's non-invertible, you may have, this periodic point may have multiple pre-images. One of them is the point that comes from the orbit itself. But like here, 0 has one pre-image which is 0 itself, but all the other points are also pre-images of 0, and they're pre-periodic points.
So here, f of k or f just as a subunit?
For some k, if the image, if fk of x is periodic for some k greater or equal to 1. If it lands on a periodic point, yes. Okay, so here everything just maps to 0. Okay? What are the other cases? What about lambda between 0 and 1? So I'm already helping you by classifying the various lambdas. So lambda between 0 and 1 is basically the case we looked at already. Okay? And again, you just have here fn of x is equal to 1 over 2 to the lambda. 1 over lambda to the n of x, right? So here you just have x0, x1, and so on. This is a factor lambda. Lambda x0, this is lambda to the n. Lambda to the n. This is x2 is equal to lambda squared x0, and so on. So everything still converges to 0. Yeah, you okay? Yeah?
Yes.
Okay. What if lambda equals 1? Sorry?
It's constant.
Then it's the identity map. Not constant. The identity map, yes? So every point is a fixed point for the identity map, right? f of x equals x. So every point is fixed point. It's an invertible map. It's also fine. These are slightly degenerate situations. The identity map in dynamical systems is a very good map for counterexamples. It's a very good to keep in mind. You know, you want to understand if something can be true, try the identity map and see what happens. And what about lambda bigger than 1? What happens here?
Only 0.
Sorry? Only 0 is a fixed point again. And what happens to this point here, x0?
Goes away from 0.
That's right, you multiply by something bigger than 1. Right? And so you go by lambda, this is x1, which is still lambda x0, right? So you still have the same f of n of x equals lambda n x, but now lambda is bigger than 1, so this is increasing. Okay, so x2 equals lambda x0, and so on. Is this all the cases?
No,
Negative.
Negative. What happens if it's negative? So let's say lambda is between -1 and 0.
Flips, start approaching 0.
Exactly. Yeah. So it flips. So you have here you have x0, and then you have x1, which is still equal to lambda x0, but lambda is negative, so it's gone negative, and then you multiply by lambda again. So you have here x2, x3, and so on. But of course, the absolute value is still you still have the same formula, fnx equals lambda nx, and the sign of this is flipping, but the absolute value is converging to 0. So this sequence is still converging to 0. And the same thing, obviously, in the other cases. So when lambda is equal to -1, then what happens? They flip, so they're periodic of period 2. Every point is periodic of period 2. Okay? And if they're greater than 1, then the same thing happens. They flip, but they're moving away towards infinity. Okay? So these are linear maps. These are, in some sense, the simplest examples of dynamical systems. And now that we have these examples, let me introduce another definition that we will use to describe a little bit what happens when points are non-periodic. So we define the omega limit set. Omega set omega of x. So sometimes I use x and sometimes I use x0. Forgive me, okay? They mean the same thing. It's just when I'm going to use the notation, I'm going to show x1, x2, x3, then I use x0. But x0 is just a choice of initial condition, right? So in general, if you take any point x in your space, the omega limit set is the set of accumulation points of the orbit, right? So we have the orbit. Here is an infinite orbit, and here the set of this orbit converges to 0. So 0 is one of the limit points of the orbit. Right? In general, there may be many limit points. We will see some more examples. But this we can write as a set, of limit points of the forward orbit of x. Or sometimes it's written like this. There's also this little bit more formal, if you want, the set of points y, such that fni of x converges to y for some subsequence ni going to infinity. This is the same thing as this, right? So saying that it's a limit point of a sequence, saying that there's a subsequence that converges to that point. Okay. And similarly, we define the alpha limit set if f is invertible, if f is invertible, we define alpha of x is equal to the backward orbit, right? It's the same. So limit points of the backward orbit of x.
This is a full orbit or like backward?
The forward orbit, the backward orbit, you just go backwards.
Like
In other words, you take f minus 1.
in this case, f is invertible.
Yes, if f is invertible,
Oh yeah.
then you define the alpha limit set like that. It's really just the omega limit set of f minus under f minus 1. It's the same thing, right? To go forward and backwards. Okay, so in general, this is the fundamental tool because just giving the definitions, it's easy to define what a fixed point and what a periodic point is, right? But if the point is non-periodic, then by definition the orbit is infinite, right? Because if the orbit was finite, it meant that it was repeating and therefore it would be periodic or pre-periodic, right? But if it's not, then it's infinite, and then the question is how do you describe, in some sense, this orbit? Now, either you describe it by giving every single point of the orbit somehow, okay, which in some cases it's a bit difficult, or you need a little bit of extra structure here. Intrinsic in this is the fact that we have at least a topological space, or metric space, or a topological space, because you need to talk about the limit of a sequence. And then you say, well, if I have an infinite sequence, which is the orbit, maybe I'm not so interested in every single point of the sequence, but I'm only interested in where this sequence accumulates, in some sense, where this sequence kind of goes. For example, in this case, maybe I can say, well, I'm interested in what happens when you iterate these maps, and maybe I'm not that interested in exactly the position of x1, x2, x3, and x4, but if I look at it asymptotically, I'm interested in eventually what is that orbit doing, right, asymptotically. And in this case, asymptotically, it's converging to 0. So what is the omega limit set of x0? Is 0. Okay? So another way of saying that it asymptotically is converging to 0 is saying that omega x is equal to the point 0 for all x in R. In this case. Is that clear? Yes? What about the point 0 itself? Is this true also for the point 0 itself? X equals 0? Yes, right? Because even if you have a fixed or periodic point, you can still think of the orbit as being an infinite sequence. It's just that this is an infinite sequence that consists of a finite set of points that keep repeating, right? So the only limit points of that sequence are the point itself. If you have a periodic orbit, if x is periodic, what is the omega limit set of x?
The orbit
It's what?
up to k.
It's the full orbit. It's the periodic orbit is the omega limit, yes. Because if x is periodic, then it will visit infinitely many times each point on the periodic orbit, and so there will be a subsequence converging. You just take the ones where it falls on this point, and every point on the periodic orbit will be in the omega limit. I think there's exercises for that, okay? So I'm saying these now, but it's really important that you write it down. You write these things and you feel completely confident, because these are really the fundamental concepts that we have here. So what about here? What is the omega limit set of a point x here? When you have the identity map, is itself, what we just said, right? So if it's a fixed point, then it's just a point fixed itself. What is the omega limit set here?
5 for x not 0.
Sorry?
5 for x not 0 and 0 for x equals
5, what is 5? Empty set. Empty set, that's right, it's empty. So this, because this space is non-compact, it just goes to infinity, it's empty. That's right, for x different from 0.
We won't allow extended real numbers?
In this case, we just have an infinite space. There's no accumulation points. If you think about it, there's no accumulation point. There's no. Okay. If the space is compact, then this is also one of the exercises, but it's kind of trivial. Then every point has a non-empty omega limit because every sequence has some converging subsequence, like compactness. Okay? So this course will be a lot of applications of topology to real life somehow. Okay? But it has alpha limit. What is the alpha limit set of these points?
0.
Exactly. Okay? So these two are kind of symmetric situations exactly, right? So here you have omega limit, but if you go backwards, you don't have alpha limits. Whereas here you don't have omega limits, but you have alpha limits, right? So alpha limit of x is always equal to 0. And here you have that the alpha limit set of x is empty.
I think that these two situations are, the functions in these two situations are inverse to each other.
They're inverse one of the
The
other.
alpha limit of a set is the omega limit of the inverse function.
Exactly, yes. Okay. Here, when you have fixed or periodic points, then both the alpha and the omega limit set are the same. Like they're the periodic. Okay. Is okay? Okay. So now we define, using these definitions, let me make one more definition which will be interesting, which is saying that a fixed point P in X is an attracting fixed point if there exists a neighborhood U of P such that the omega limit set of X equals P for all X in this neighborhood. In other words, like in this example, so because you have a dynamical system now, in these examples, this neighborhood is all of R. Whenever you have a point, when you have lambda between 0 and 1, everything converges. Everything converges to the origin, which is the fixed point is 0. But the more general setting, when you have a more complicated system, you might have a fixed point here, and there might be some neighborhood U here, and you know that every point in here, it converges to P. So it's omega limited set in P. And then we say that P is attracting. Okay? Or sometimes you say that it's a sink. So wait. Sometimes we say that P is a sink because things sink into this. Okay? And similarly, P is repelling if there exists U, okay, such that alpha of X equals P for all X in U. So there's some fixed points that are attracting in this way, that the points nearby attract in forward time. If it's invertible, you can also talk about, sometimes this is called also a source. Source, because this is where things come from. So things, in some sense, intuitively are moving away from this point, right? But the way to formalize that is to say that in backward time, they're moving towards this point. So these are the two fundamental definitions. Okay, so now we can move on to the first of the two classes of more sophisticated examples. Now let's suppose our space X is S1, the circle S1. Now what do What do you know about S1? So there's various ways to define S1, just a small little diversion, right? Sometimes you think of it as a unit circle in the plane, or you can think of it as the quotient R over Z. You know this definition? Okay? This just means that you think of it as the unit interval with the endpoints identified. The only difference is that we think of the length of the circle to be 1 instead of 2 pi. Okay? It's much more convenient for us to think of it that way. Okay? So we think that we have a kind of a special point here which is 0, and then the length of this is 1. It's like, as you take this is 1/2, okay, and you think of this as being, in fact, sometimes you even draw it like this. It's just the unit circle 0, 1 with the equivalence relation that 0 is equivalent to 1. The unit circle. And now we can define a map or a class of maps. Let me call f theta f. Maybe I should call it here. So we use x. F theta of x is equal to x plus theta so the phase space of the unit circle is, so if you start with some point here x 0, okay, then you apply f, so you're adding theta x1, so this length here is theta, right? And then you apply f again, so this length here is theta x2, and then what happens when you drop off the other side? You come back the other side because you're on a circle, okay? So you take this length plus this length, you get another point where the combination of this plus this is theta, right? It's as though you're starting here and then you go here, x0, x1, x2, and then x3. So the way we write this is mod 1, just to be clear about what we mean, right? So we're taking a point between 0 and 1, we're adding theta, and the result that we get is the number mod 1, which means you ignore the integer part, right? If you were really to make an addition, you get 1 plus something, you ignore the 1 and you just have the plus something. Okay? Good. So now we have a map on the circle. Is this an invertible map? It's an invertible map. It's just a translation by an angle theta, right? You take every point, you apply this map, you take every point and you just shift it by theta. So you just take the circle and you shift the whole thing by theta, okay? So now we've chosen a specific initial condition. We shift it by theta, shift it by theta, shift it by theta, and so on. So what's going to happen to this point? So we would like to, theta is not a good because I've used theta for the orbit. Sorry, let me use alpha here. Sorry.
Maybe it's also
I've
already used alpha for the alpha limit. Beta. Okay. Gamma, lambda. There's not enough letters for everything. So this is beta. Sorry, you can leave theta if you want that. It doesn't really matter. But I just want to remind that we have the orbit here. Let's look at the forward orbit. Okay, it's more convenient. Forward or backward, it doesn't matter. But let's just look at the forward orbit of x. As we said, is a priori an infinite sequence, which might repeat. But fn of x for n equals 0 to infinity. So what does this orbit look like? What is this doing? What is this compared
If it is rational,
Sorry?
It depends on beta whether or not.
rational or irrational.
Rational or irrational number?
If it's irrational, then it's the whole space.
If it's rational,
Irrational, then
if it's irrational,
it's the whole space.
what do you mean by the whole space?
It's dense.
The set is dense.
The circle.
So good. A lot of good observations. So it cannot be the whole space because it's a countable set. The orbit is a countable
Yeah, I
field.
mean,
You mean that it's dense in the whole
It's dense.
space. And how do you know that?
If it has period, so some n beta is equal to integer number, and it's so beta is irrational. It's a contradiction to suppose if
Okay, so this is one of the exercises. It's one of the key exercises now. You can prove that, okay? But that's correct. So the theorem really says that alpha is rational, beta rational if and only if every point is periodic. Every x is periodic. And beta is non-rational if and only if every omega x, let's use the notation we have, omega x equals S1. Right? That's what we mean by dense, because every point on the circle is an accumulation point of the sigmas. That's what dense means for all x in S1. So I will leave it as an exercise. It's quite easy. Certainly the rational is very easy. The rational, you just literally plug in a rational and you see that it means that at some point this must be equal to 1 mod 0, and so you get this property. Okay, the irrational is not completely trivial, but it's just a few steps that is guided in the exercise there. So what do I want to say more about this particular example? Yes. So there are many. Okay. So this is the theorem. This is a second example in which I guess the new characteristic is that we have an omega limit set that is non-trivial. You can have these situations where the orbits are dense in your space, which is very remarkable. Okay. So I think usually I like to take just a couple of minutes break. So why don't we take a couple of minutes just to rest, because then I want you fresh again for the second half of the class. So, okay, so now we come to my third and most favorite example, which is the following. Now we take x equals 0, 1. And we take f of x equals 10x. And again, if you multiply by 10, you might take a point between 0 and 1, which is...
Sorry, but this goes out to...
Exactly. So, exactly. So here also we want to take more 1. This is the key point. Because remember that the map 10x we already, on the whole real line, we already discussed before. Okay? So the key innovation here is that we're going to take mod 1. And this is going to make a huge difference, okay? Because things on the 10x, they're trying to escape to infinity, but every time they escape a little bit, we bring it back, okay? And we will see what's going on here. So I think the nice thing here, you will see why I choose 10x, because we all know how to multiply by 10, even in elementary school, okay? It's the easiest multiplication. So let's, before we look at the geometry, let's literally try to apply this map to some point, right? So let me take an initial condition x0. So I can draw the interval 0, 1. Okay? And then I take some x0. And let me just try to get a feeling for what's going on. x0 equals 0 point, what is this, maybe 7, 1, 2, 9, 3, 5, whatever. Decimal expansion of x0. Every point has an infinite decimal expansion. Yeah. So what is x1? So f of x0.
1.2.029.
Okay, easy. So we multiply by 10. We drop the 7 because it's mod 1. And we get 0.12985. x2, 0.2935. Let me forget about the 5. There's too many things otherwise I have to do. Okay, x3 equals 0.93. x4 equals 0.3. x5
Depends.
0 or 1?
It depends if it's rational, irrational, it may be
But
very
it depends, but what does it depend on? Just on one thing, easy thing.
The next,
Exactly. It just depends on what we had here. That's what we would get here. Right? Then of course, as you keep going, it will depend on all the digits. Okay? They're there, but we just don't know what they are. Okay. Now there's a lot of remarks to make about this particular system. It's a very interesting because
Sorry, one is inside of this set or not? One is
yeah, that's a good question. One is kind of vague because strictly speaking, when you take mod 1, you're identifying 0 and 1. So maybe I should be more precise and write it like this. If you want, if we take mod 1. Yes, correct. Sorry?
This is quite interesting.
Yes, this is a very interesting map because,
For example, 1/7 would be periodic.
okay, so good point. So let's talk about the fixed and periodic points. What fixed points does it have? So before I have some general comments, very interesting comments made. But let's first correct. So the first question, now that we know how it works, okay, we can start looking for fixed and periodic points, which are the basic objects. So fixed points. One fixed point is obvious. 0. 0 is a fixed point. What are the fixed points? Any other fixed points?
No, point 1,111, point 2.
Yes, thank you. Okay, fixed point 0. 0.111111. Recurring. You see that that's a fixed point, right? And then obviously all the others, right? 0.222 and so on. So there's 9, yeah, depending on whether we put 0.999 in there.
Yeah, that's
Okay, but anyway, all these are fixed points. Okay? Periodic points.
periodic would be the numbers of repeating digits.
Exactly. So 0.34, 34, 34, periodic.
Yes.
So 0.34 periodic. This is a periodic point, yeah, of period 2, because when you take the image, so this is 0.34, 34, 34, and so on repeating. You apply F and you get 0.434343, and then you apply F again and you get this. Periodic point of period 3, easy, right? 0.592, repeating, period 3 in the same way. So how many periodic points are there?
How many are there?
Yeah, infinitely many. Countably many, because they're all the possible combinations of finite digits, basically. If I want a periodic point of period 100, you just give me any 100 digits, and I stick them in here, I repeat, and I get a periodic point of period 100. Where are they?
Where are they?
What can you tell me about the set of periodic points? Sorry? Is it dense? It's dense, you're saying? Is it dense?
Yes, because it could be called the rational.
Periodic or
Not
pre-periodic. For example, rational numbers are pre-periodic.
Okay, so we're mixing two different things. Okay, so let's first of all, okay, let's talk about the pre-periodic. So if x is rational, then what does that imply? That it may be periodic, or it may be fixed point, periodic, or as you say, pre-periodic, right? Is every rational number one of these cases? Yes, because you know almost the definition of a rational number is that it has a eventually periodic, right? So x in Q means x is pre-periodic, is either periodic or pre-periodic. Okay, because rational always means that it has a repeating sequence. So you may have something of the form x equals 0.3712, and then you have this 592 repeating. Because this map is non-invertible. Why is it non-invertible?
Because we can append any number before the one we have.
Exactly. Because here, if you see, this point here has this point as its pre-image, but it has also other points as its pre-image. You can put a 1 or a 2 or 3 or 0, any digit here, and it will give this point as a pre-image. So actually, every point has 10 pre-images. Let's draw the graph. It's a good moment to draw the graph of this map, which can be useful. What is the graph of this map?
9, not 10.
Sorry?
10, not 9. 10, because it can be
10 pre-images, yes, 10 pre-images. Sorry, that's what I meant. So what does the graph of this map look like? What is the derivative?
Here straight lines. It looks like from 0 to 1 over 10 and 1 from 1 over 10.
Exactly, because the derivative is 10. The slope is 10, because this is just 10x, right? The only thing you're doing is when it gets too big, you're shifting it down, right? So if you think of starting with just the linear map 10x, starting from 0, it goes up with slope 10, okay? So it reaches the top exactly the point 0.1, right? And then this bit here that should be up here, you just translate it down, because by taking mod 1, you're just translating it down, and so you get another straight piece here. And the same thing, this wants to continue, but you translate it down, okay? And so you go all the way, this is 0.9, and here you have another branch in some sense. So you have 10 branches, each one maps to the whole thing. And if you take a point here, like this one here, 0.1293, somewhere here, 0.1293, whatever, you see that it has all these pre-images, right? These are all points that map to this, depending on the digit that you had before. Right? So this would have a 0 before the 1, this one would have a 1 before the 1, and so on. So you can see from the graph, you can see how each point has 10 pre-images. But from the graph, you cannot do the analysis that we're doing now. So this is interesting. So the graph does not help so much to understand what's going on, and we're going to develop several techniques to understand that. So the question I had, the first non-trivial question was that whether the periodic points are dense. The periodic points are dense. Why are they dense? What does it mean to say dense? It means I may take a point here. Okay, sorry. First of all, let's establish that if x is not in Q, this means that x is neither periodic nor pre-periodic. Okay, so in some sense this is a if and only if. This is also all in the exercise, okay, so at home you should verify all this. But x is rational if and only if x is either periodic or pre-periodic. You can check that. So if x is not rational, then this means x the orbit is infinite, right? The x is infinite. So we're going to study a little bit, try to understand a little bit what the possible structure of these orbits are. But first of all, so if you take a point here, an arbitrary point here, z, if it's rational, then it's periodic or pre-periodic. We've established according to this. To show that the periodic points are dense, we need to say that if it's not rational, then we can find arbitrarily close a periodic point. Okay, I guess we've done it because we know that the rationals are dense. But can you give me an argument that does not use this fact, just from the
Because we can take
the dynamical
to cut at some point.
And repeat.
Yes.
Exactly.
We can cut arbitrarily far as the decimal expansion.
Exactly. Is that clear for everyone, right? So you can take z is some point that has some decimal expansion, right? z1, z2, z3, and so on, some infinite decimal expansion. Okay? And now we cut off the first 1,000 digits of this, and we repeat. And we make a periodic orbit that has the first 1,000 digits repeated. Then it's a periodic orbit of period 1,000. And because it's the first 1,000 digits are the same, it will be very, very close to z. However close you want it to be, you can take the first 1 million digits and start repeating those, and so you will get a periodic orbit that is arbitrarily close to z. Okay, so you can show this. They do not have to be pre-periodic. So maybe I could have insisted that I want specifically the periodic points to be dense, and not the periodic and the pre-periodic. Okay, so you cannot use the argument that the rationals are dense. So this is just the periodic points are dense. Okay, very good.
Sorry, how do we know that the rationals are eventually periodic? This is because this is not how we define the rationals. We define the rationals in terms of integers.
Fraction, in terms of fraction.
Yes.
And then if you think about it, every fraction, when you write the decimal expansion of a fraction,
You can compare from data is equivalent.
when you always write a decimal expansion of a fraction, 0 point, then it comes out as
I don't think that every fraction has a repeating decimal.
yes.
Eventually.
Yes, eventually.
0, 0, 0, 0. It can be eventually.
An example of 22 was 7, Louis.
7 is known.
It's an elementary thing which at the moment I cannot remember how to do, and I cannot. It's an elementary thing you can find. It's really elementary to show.
What's your question? That every fraction has
Every fraction has a repeating decimal.
This
Eventually.
eventually.
in other words, every rational is pre-periodic in this sense. Wagner, you remember how to do this? You can look it up. If there's a problem next lecture we can address it, but it's really a very elementary thing. Decimal, in the theory of decimal expansions. Sorry, it's so elementary that I did not think that I should know the proof, but you're right, I should know the proof of that fact. Now, let's concentrate now. So this, in some sense, takes care of all the rationals, takes care of all the periodic and pre-periodic points. Okay? But as you know, the rationals are a countable set. It's a very small set, in some sense. From a dynamical point of view, what's left is very big. Most points are irrational. So what is the dynamics of an irrational point? What is the omega limit, for example? Can we find a point whose omega limit, so question, does there exist x such that omega limit of x is equal to the whole space? And second question, does the exist set X such that omega limit set is not equal to the whole space. So I'm not sure how much, this is again one of the key exercises, I'm not sure how much to...
The second equation is trivial because if I take a fixed point, it can't be.
Yes, okay, let me take irrational. That's what I meant. Irrational points.
Nothing Q.
Sorry?
This is nothing Q.
Not in Q, not in Q, yes.
The first one.
Both of them are
It's
not
not
in Q.
It's not in Q. Both.
I'm not going to look at the irrationals, okay? The rationals are obvious. They're either periodic or pre-periodic, so they have a finite omega limit set. They all have a periodic orbit as an omega limit set, if the point is rational. Because either it is a periodic orbit itself, or it eventually falls onto a periodic orbit, so that's the omega limit set.
If we take all the rationals, we can list them, right? Because they are coupled. I'm
So-
just trying to answer the first one.
Yes.
Yes. If I take all the rationals and list them, and I list them in a sequence, I list them in the decimal expansion of them, and I concatenate all of them. I
Yes.
get an infinite number.
Yes.
This number, if I take all the omega of it, it would contain all the
Yes.
rational numbers, and therefore it is there.
Yes. Correct. Correct. But I don't think I want to go through it now because I'd like everyone else to try to figure
But
it out.
how do we put them right after each other if they're
Because every one of them is finite. Okay, I can take only
It's
the
not-
rationals which have finite decimal expansion.
No, you don't take the rationals, you're right. You take all. I don't know if I should tell you or not. You want me to
Finite
tell you?
decimal.
Let us figure it out.
Figure it out. You basically got it right, yes, but you did not say it exactly the right way. Yes. So I think you should work on it, but it's to do with this. You need to have an orbit that accumulates all the other, who has subsequences that comes arbitrarily close to every other point. The second part is very easy. How do you make sure that the omega limit set is not? So when you, in fact, really, I should have asked them the other way around because this one's easier, but both they're slightly different arguments. But this just wants to make sure that you do not cover everything. So suppose I want to make sure that this point never enters the interval 0.5, 0.6.
So let's we can take an irrational number in this set, whose digits are always in this.
Whose digits never contain 5.
Yes. Bigger.
Whose digits never contain 5, right? So the crucial, let's go back, because you see, I told you everything is simple here, but be careful, because suddenly things get a little bit subtle. So let's go back to this example, right? Notice, where are these various points, right? 0.712 is somewhere here, then 0.1293 is somewhere here, 0.293. So you see that if you have a 3 here, okay, then eventually this 3 is going to come to the beginning of the sequence. And that means that this point lies in the interval 0.3, between 0.3 and 0.4. Okay, so there is a connection between the geometric structure here and the position of the orbit. Even though this orbit is jumping around very much, you know that if you look at the point 3 here, then after 4 ellipses it's going to be in here. Okay, so now if I take something which is irrational, but the number 3 never appears, then this point will never come inside here. And there are lots of irrationals like that, obviously. Right? So it's the other side of the coin. in what you were saying, I've forgotten your name, sorry. Yes, what you were saying is that to get this, you need to make sure you have all finite blocks in the decimal expansion. Okay? If you're missing one finite block, then you lose it, because this works also for 9-3, right? Suppose now that 3 exists and 9 exists, but you never get 9 and 3 together. Okay? Then also the orbit is not dense, because this means that between 0.93 and 0.94, okay, when you have a 9-3 together, at some point you will come here and you will get 0.93, which means that you are between 0.93 and 0.94. Yes? So if you make sure that in the sequence you may have all the digits occurring, but you never get 9 and 3 together like this, then already the orbit will not be dense, because at nowhere will you ever get 0.93, which means that never will you enter this little tiny interval. Yes?
Posso falar em português, que é mais rápido?
No, I think you should make an effort to speak in English.
After I thought the answer with previous question, but in English it's complicated.
Fine.
Ok. Não, só é você dividir o P pelo Q e pegar a expansão decimal e escrever como uma série, né?
Ok, depois nas classes de exercícios você explica isso. He was just having a solution to the P over Q, to the rational numbers, right? I said in the exercise classes you can go through it together. Yeah. Okay, so you can see the mechanism. In some sense, the mechanism, the easy mechanism for this gives you exactly the clue for this, right? Is that if there's ever any finite sequence that is missing from the decimal expansion, then the orbit will not be dense, because even if you take a finite block of 5 digits, then when those 5 digits, they define a little small interval, which are all the points whose decimal expansion starts exactly with those 5 digits. If that sequence of 5 digits is missing, then the orbit cannot be dense, because you will never get those digits at the beginning of the orbit. Okay? So all you need to do to get a dense orbit is make sure you get all finite collections of digits. And that's easy because it's accountable. You just take 0 to 9, and then you take all the ones with 2 digits, and then all the ones with 3, and so on, and then you get the dense orbit, many dense orbits. Okay? So one final comment about this map also is that this is an example. This is an example of a chaotic map. Why is it an example of a chaotic?
Because you move a little bit in a fixed point. For instance, you can get a thing which is not quick.
Yeah, so sometimes, to be honest, I will not give a formal definition of chaotic also, because I think that there are some attempts to give topological definitions, but I don't think they're very meaningful or very relevant. But the spirit is, and in the second part of the course, when we talk about the probability theory and measure theory, this will be one of our main examples. We will study this in quite some depth, and we will be able to say some very interesting things from a statistical point of view. But from a topological point of view, the general feeling is, the general intuition behind chaotic is like this, is that it's got what's called sensitive dependence on initial conditions. Sensitive dependence on initial conditions. What does sensitive dependence on initial conditions mean? Suppose we take another point here. We'll just give an example. Suppose we took another point which is 0.71301, for example. Let me put it here. How close is this? These 2 points. They're very close. Well, I could even make them closer. Anyway, you will understand what I mean, okay? This is 7.129 here. This is 7130. it's kind of close to 3 or 4 decimal places, something like this, okay? Which is in some sense very close. I could do the same with 6 or 7 decimal places. What happens as you iterate here, so y1 is equal to 0.1301, y2 is equal to 0.301, okay? These are still relatively close. This is 293,301, but what happens
Can be in.
to y3 is suddenly 0.01, and this is 0.93. Now suddenly 1 is here and 1 is here. Suddenly. Why is this happening?
Because after that we can put any numbers we want. Because
We're not looking after that, we're just looking after that. Right? So we started with 2 points that are very, very close, and within just 3 steps, they end up on completely opposite side of this. Okay? I mean, the kind of technical explanation is simple. When you multiply by 10, you are stretching the distance between 2 points, right? And in fact, you see that even though this point, these 2 points are still quite close and these 2 points are still quite close, they're 10 times further. These 2 points are 10 times further away than these 2 points were. These 2 points, you're stretching them. When you look at the graph, we had the graph that was like this, right? You take 2 points here, and their images are 10 times, because the slope is 10. Right? So this 10x is really moving them further away in a way that's much more dramatic than you would initially think. Okay? And the effect of that is that you end up after very few steps with 2 points that are completely far away from each other. So one of the reasons why this is interesting is because it connects to a lot of phenomena in the real world, okay? There's the simplest that I like to quote is just when you toss a coin, okay? When you toss a coin, right, and we use this, is this a random system or is this a deterministic system? Coin.
Deterministic.
Good, I like it when there's a bit of debate. Random or deterministic? How many people think it's deterministic? How many people think it's random? How many people are too scared to say what they think? So, this is used almost universally as an example of a random system. You say, you even use it as a like coin tossing is like random, 50%, 50%. But look at the physics of it. What is random about the physics of it? I have an object, I apply a force.
The initial conditions?
The initial conditions are this, the force that I apply, the position, and the outcome is absolutely determined by the laws of physics, given those initial conditions. Classical mechanics, there's no quantum mechanics here, okay, it's just really this. So why is it unpredictable? But why physically is it unpredictable? I mean, really, why is it unpredictable? Since I am the one applying the force.
Because it's sensitive.
In what way is this sensitive? What is sensitive about this actual physical system?
I mean, the force, the weather.
Yeah, but the main reason is really the mechanism we use to apply is not very controllable, right? Because of literally the way you flip, it's very hard to control very well how much. So you're right, we cannot really control the initial conditions, that's the thing. So we don't know exactly what the initial conditions are, because if you put a machine that always gave exactly the same force in the same place, you will get exactly the same outcome. Okay? Unless it's exactly so that it falls like that, but basically you'll get the same thing. There's nothing random or about this, okay? Nevertheless, it's unpredictable. Why? Because of the initial condition. So in that sense, it's very similar to this. So the predictability is not because the system is intrinsically non-deterministic, but it's unpredictable because and not because we don't know the physics of it, right? But because we don't know the initial condition. It's very hard to control the initial condition, okay? And here it's a very nice, simple mathematical example of a system that is completely deterministic, because if you choose a point, its orbit is completely determined, right, by it, the point. The point has an infinite decimal expansion, and as you can see here, the images of the points are completely determined by the decimal expansion of that point. It has a certain decimal expansion, and this will determine, if I know what the 1000 decimal place digit is, then I will know that after 1000 iterates it will be here or here or here. I know where it will be if I know the 1000 decimal place. But if I only know the point approximately, then very, very quickly I lose the predictability, and already you could see here that I didn't know, because I didn't know the 6th decimal place after 5 or 6 iterates, I don't even know where it's going to be. It could be anywhere. Okay? So, in some sense, this was in the kind of history of dynamics. Dynamics goes back to Newton, really, to differential equations, and Newton is a very, very classical subject. But it really, in the last 50 or 60 years, it really kind of stepped up a gear when people realized this, and realized that in physics there's many systems that have this unpredictability. The weather is the classic example that everyone uses, right? Why is it difficult to predict the weather in 1 week? It's not because we don't understand the physics of the weather. We understand the physics of the weather very well. But we don't know the initial conditions so accurately. There's the famous story of the butterfly. You know the story of the butterfly that flaps its wings. There's an anecdote that said, well, a butterfly flaps its wings in Brazil, and then, 1 week later, there's a tornado in Florida. Okay? It's not, of course, exactly like that, but it is pointing out this. So you forgot to know that the butterfly flapped its wings, so you forgot to know that at the 100 decimal place, there's a 5 instead of a 1. Because you didn't take into account small thing. Okay? And that small variation in the 10th or 20th or 30th decimal place, after a little bit amount of time, it makes a huge difference to the outcome. Okay, this is what sensitive dependence on initial conditions are. And so this is a class of examples, and this is the simplest example, but there's many, many, many classes of mathematical examples which have the sensitive dependence on initial conditions. And this will be the main, as I said, the main object of study in the second part of the course, because the second question, of course, is if you cannot control it, why, when you flip 100 times, are you very likely to get very close to 50-50 chance? Okay? This seems obvious to us because empirically that is true, but the theoretical justification of this is far from trivial. Each time you don't know what you're doing, you're getting a heads or tails. A priori, why shouldn't you, by instinctively, more times give the amount of force that you need to get heads, or more times tails, or why should there be any kind of statistics to that, right? And so we will study at least from the point of view of mathematical model. I'm not clear that there is a physics explanation of this fact, but from a mathematical point of view, we have theorems that tell us, for example, that in these cases, the proportion of 7s and 1s and 2s, they are 1/10 of the time you get 7, so there is some statistics in this, even though it has very complicated topological behavior in some sense. Okay, so I think this is roughly the main fundamental examples, the main notion of dynamical systems, and a little bit of a feeling of the kind of problems we will be studying as we go along. Okay? So I think for today is okay. I will send you the notes. Again, please keep in mind that we're not going to do all the notes, and keep in mind that these are just draft notes, so they may contain mistakes, they're not complete, and so on. They're just to help you out. Okay? And please make sure you do the exercises, they're really important. Okay? And okay. Thank you very much. See you next time.